This last video hopefully helps to explain the other little bit of weirdness and really the reason why we learned all about the S, the P, the D, the F. We learned about our orbitals and our sublevels, even though we used Bohr models most of the time for trends. So the ideas of levels is enough to explain almost all of the trends. It explains shielding, it predicts Zeph, and shielding and Zeph can let us know what will happen with size, what will happen with electronegativity, what will happen in general with ionization energy, and then how that turns into reactivity. The problem is some of these little weird things. We said this goes up, 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 but it doesn't. We go up, down, up, up, down, up, up. Overall, our trend is increasing, but there are a few patterns in our trends that are broken. You won't have to memorize each one, but we want to use electron configuration. We want to use PES to explain and understand them. And you will have to choose the exception when given the right data. So, one of our exceptions here is why is aluminum lower than magnesium? We very intentionally in our notes didn't choose aluminum and magnesium, but we chose the other elements that are in those same columns because anything that we see in the top of one column follows the same way down the whole thing. So we should expect our ionization energy to get higher and higher and higher each time I add more protons. But when I go from beryllium, I have a ionization energy value of zero point 0.9. The easiest electron to take away from boron is 0.8. Or here in a different unit, because these would be in megajoules, these are in kilojoules, it goes from 700 down to 500, the same families. Well, the idea here is that beryllium is over on, you can't see my hand, this side of the periodic table. Its electrons are in the S sublevel. Right over here, when we talk about boron and we talk about aluminum, we are starting to fill another sublevel. They're fairly close in energy, but the Zeph and the shielding, especially the shielding, doesn't perfectly predict that those electrons are in subtly different sublevels. To leave it off as just a ring without that idea of sections within the ring doesn't perfectly predict why sometimes we can remove an electron a little bit more easily. The other, we did go up, 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 up. So we're doing good there. We went up. The other time it went down was from phosphorus to sulfur. All of those, and those guys are right here on the periodic table. Anything else in that same place on the periodic table would have that same weirdness. They're really close to each other when they should be going up. So here we can see that in terms of carbon to nitrogen, but really nitrogen to oxygen. Nitrogen has a certain value. Oxygen should be higher because it's got more protons, but it's that tiny bit, a tenth lower. Sulfur should be higher. It's got more protons, but it's a tiny bit. It's, in this case, 10 lower. That isn't explained just by going from like an S to a P or a P to a D. That has to do with how we fill our levels and our sublevels. So right here, we remind ourselves that we can write things as 1s, 2s, 2p. We can do noble gas notation. But sometimes, and here we have the empty and then the filled in versions of the orbital diagrams. Carbon puts 2 and 2 and 1 and 1. Nitrogen follows all of the rules. It spreads out before it doubles up, like Hund's rule said. But oxygen has nowhere to put its fourth electron without doubling them in there. So even though we know that we have more protons, we know that we have more Zeph, we haven't changed our amount of shielding, the fact that we're cramming two electrons into the same place means that there's a little bit of an exception there or a little bit of repulsion. Those electrons are pushing up each other apart. and they don't attract and stick in there quite as well. That electron is unusually easy to take. So we won't have to memorize all the ones that do this. It is good to understand why, but what we're really looking at is when the pattern should do one thing. This goes up, that goes up, this goes up, that goes up, this goes up, remembering that there is a part of our structure of the atom that explains why this goes down. Or when this goes down, remembering that those two sections within the sublevel help to describe it. This is only an exception or only significant really on our first ionization energies. We'll see that there isn't quite as many exceptions as we go to second, thirds, and fourths.